In the chemistry class, we often show reactions in one direction. That is, we might take a reactant, and heat it up and decompose it. Or we might take two separate substances, bring them together, and synthesize a new compound. But we don't always show both the forward and the reverse process separately. And that's one of the things that I'm going to show now, and that is I'm going to show a reaction in forward direction and then also in the reverse process. In addition to that, the reaction that I'm going to illustrate here is one that one could also use when discussing acid bases and their reactions, and in particular Lewis acid, Lewis base reactions. Those are ones that are discussed in an AP chemistry class, but not often shown to students. So we're going to take a look at the reaction of copper 2 sulfate, and we're going to take both the hydrated form and react it, or try to react it, and the anhydrous copper 2 sulfate and react it, or try to react it. Now, if in your chemistry storeroom, your stockroom, you don't have the anhydrous copper 2 sulfate, one can easily make that from the hydrated form excuse me, by taking the hydrated form and heating that up gently using Bunsen burner and allowing that to cool. And we can go from the hydrated form, which is a very pretty blue crystalline substance, to the anhydrous compound, which is a white powder. Now, one of the reactions that I'm going to show is the reaction of the anhydrous compound. And first I'm going to show that with water. And I have some water in a beaker right here. And I'm going to take one of these test tubes with the anhydrous copper 2 sulfate. I'm going to take some water. And I'll add that to the anhydrous Now, in doing that, you might hear water almost boiling in there. In fact, I can see that it is boiling, and it is because it's generating a lot of heat. That's a very exothermic reaction. If you do this on a smaller scale, such as in a Pasteur pipette, put a little bit of the anhydrous compound in that, you can let students hold the sides of that Pasteur pipette, and they can experience just how much heat is generated by a very small quantity of the copper 2 sulfate. Putting my fingers just touching that, I can feel that I would not be comfortable holding that test tube for very long. It's a lot of heat generated. That's the anhydrous copper 2 sulfate with water. Now I'm going to try it with ammonia, and I'm going to use gaseous ammonia. And I have that here. And this works best when you have fresh concentrated ammonia. Doesn't work well, if at all, with anything less than concentrated ammonia. I'm going to take a sample of the gaseous ammonia from above the liquid using a syringe. Okay, and I have a valve here, a one-way valve, and after drawing up the ammonia, I'll close the valve, close the cap to keep the fumes as best I can, keep them in the bottle, and then I'll react the ammonia with the other sample of the anhydrous copper 2 sulfate. And this is a brand new bottle. get a syringe full. And I'm going to open up the valve and slowly push down on the syringe. Stopper it. Now, I know not as much heat is generated in this reaction. Now, at the very top of the test tube, you can see a blue color of a copper-2 ammonia complex ion that's been formed. I'm going to shake this once again. Then I'm going to add a second sample of ammonia to this. So I have now, mixing this up, I have a blue tint to that. I'm going to do this one more time. Could point out to students that in the sample of gas that I'm taking, I have many fewer molecules than I had of water molecules when I added some liquid water. Stopper this once again. And you can see a dramatic change in the appearance here. Definitely a physical change. And if I were to open up the stopper, say in a fume hood, let any excess ammonia, if there is any excess ammonia, go off, and then let this sit for a while, stoppered, this wouldn't go back to the original set of conditions, which is usually an indication that not only did I have a physical change, but I had a chemical change accompanying it. So let's now take a look at what happens to the copper-2 sulfate, the hydrated form, when I add water to it as a control. I don't hear any sound indicating perhaps a boiling of water. What I see is the start of the copper-2 sulfate, the hydrated form, going into solution, which is not unexpected on my part, but perhaps students might not know that. Okay. Touching this, no indication of any heat either given off or taken in. Seems to be right around room temp. Okay. Let's try this now, the hydrated form, with the ammonia, again as a control. Once again, we'll go to the ammonia. what I observed, and perhaps the camera can pick that up, is a darkening of the crystals of the copper sulfate. At the very top, you can see that there's a darker blue color, whereas at the bottom, it's considerably lighter. In fact, that blue color is very similar to, although it's difficult to see now because this has been mixed a bit, but the dark blue color is very similar to the complex ion that was formed with the copper 2 ion and the ammonia. Perhaps the ammonia has displaced some of the water molecules that's in the crystalline, the crystalline form of the hydrated copper 2 sulfate. And so we have that darker blue color of the copper 2 ammonia complex. Let's take a look at some of the equations. Set this aside. We started with the anhydrous form of copper 2 sulfate, which is the white solid, and the hydrated form, which is known to have 5 waters of hydration. And this is our blue color. When we added either ammonia or water, we saw a reaction. With the ammonia, we saw a blue color form, and indicating a reaction occurred. And what's formed there is a compound with a certain number of ammonia molecules that are bound in the crystalline state to the copper 2 sulfate. And we won't get into how they're bound. With water, we see a similar thing. And since I added a lot of water, I actually formed the hydrated form of the copper 2 sulfate. And a good bit of heat was generated there. With the hydrated form of the copper 2 sulfate, when we added ammonia or water, with ammonia, we got some exchange. How much? Depends on how much ammonia I added. I didn't do it quantitatively. And what's more, we'd have to do a lot of experimentation to determine just how many waters were displaced by the ammonia. So we have probably a mixture right now of this and let's suppose it's this. You can put a Y there. Something such as that. With the copper 2 sulfate, with water, what we get is a solution of copper 2 ions, sulfate ions. And that's it. So here is a very nice way of demonstrating not only a reaction which you can talk about as a synthesis reaction. We can do a decomposition reaction, which I didn't do, but you can do that easily by taking the hydrated form, the copper 2 sulfate, and heating it up. Then you can show the reverse process as I did, and that was the anhydrous form of the copper 2 sulfate, adding water to it. And as I mentioned earlier, with an AP class, you can talk about Lewis acid-base reactions because these do involve that type of reaction. Thank you.